All right, this will be good review. It's mostly review. This is important stuff to review though, before you go to college. Do a little bit of calculus, but mostly just algebra review.
It's okay.
Okay, what's it mean, real quick, what's it mean to be, a couple vocabulary words, relation versus function. What's a relation mean in math? Very, very important words. Everybody remember? Relation versus function. What's it mean if you have a relation in function, or a relation in math? All it is, a relation just means, it's sometimes called a mapping. And all it means is there's a relationship between variables that maps an independent variable to a dependent variable. Okay, so there's some, and a lot of times it's easy to think about that. It doesn't necessarily have to be this way, but it's a good way to think about it. There is some kind of a formula or an equation that relates two variables, right? Sometimes it might even just be that there's like we have data tables, and we have some x values in the domain and some y values in the range, and there's not really a perceivable equation that relates them. But a relation could be something like, maybe like this even, something like x squared plus y squared equals 4. If I were to graph that, what does it look like? Circle with a radius of 2, centered on
0.
0, 0. Yeah. So that's a relation right there. It's a relation because if I pick any x value, there's a corresponding y value, or maybe even more than one y value that goes with it, and vice versa, right? Okay, how does that differ from a function? A function is a little more specialized, and it's a little more tightly defined. What does it mean to be a function? It is a kind of, it's a subset of the set of relations. But there's something unique about the relations if it's going to be a function. What's the rule for going back to
the horizontal line test?
Vertical line test.
Vertical line test. Yeah, the vertical line test is the graphical manifestation of the definition of a function. You fill in the blanks for me. This is the rule for a function. For every value, let's just make the assumption here, just so we can be kind of visual about this, that x is the set of the independent variable and y is our dependent variable, right? For every value of x, there is one value of y, exactly. In other words, there's not more than one value of y, right? So function gives us this one input, one output kind of a thing, right? Okay. So let's look at a couple examples of functions then. Is that a function?
No.
No, that is not a function. Good, because this violates the vertical line test by having multiple intersections, right? So functions just essentially look, we had to let's draw a red one and a green one, or a green one and a blue one. How about, here's a function, right? Or, those are both functions, correct? Okay, good. All right, so we're going to start with relations here, and we're going to talk about what it means to be the inverse, what it means to be an inverse relation, and that's a very loose definition. And then we're going to tighten that up a little bit and say, okay, now what would have to happen for there to be an inverse function? Okay, so an inverse relation. Everybody remember what that is? What's the recipe for making an inverse? Recipe for making an inverse. So for example, let's just take a data table. Let's say that we're going to define this as f. These are my x values, let's say. And those are my y values. domain of that function? Say it again.
1 to 4.
Well, 1, 2, 3, and 4, yeah. These are just discrete values, right? So it's not like it's continuous, just there's only 4 values in the domain, 4 values in the range. Okay, what if I wanted to do, let's call G, we'll call it F inverse. That's our notation for inverse, right? What's the domain of the inverse? What is it again? Yeah. What's the range? Moral of the story. How do you make an inverse? What's the definition of an inverse?
Switch.
Yeah, that's all you do. Literally, that is it. You create an inverse relationship by simply interchanging the domain and the range of the relation. That's it. Okay. So what does that do? We gotta look at this on just a couple levels. Let's look at it first of all graphically. What's that do graphically? I've got a good little trick for you on this too. Is this coming back a little bit now? Last year you probably would have talked a lot about this in this. Yes. Because when you talk about logs and exponential functions, it's all based on understanding this inverse relationship. So hopefully this will just kind of come flooding back into the memory banks as we talk about this here a little bit. If we graph, let's take something like, how about, we'll just take y cubed, or x cubed, sorry. This will be our relation that we're starting with. So f of x equals x cubed. Okay. If I want to graph the inverse of that, what do you suppose the inverse is, by the way, you know? We'll find out here in a little bit. You want to have a guess?
No.
Okay.
No.
That's fine. To graph the inverse, though, do you remember the kind of symmetry that the graph has? Any second now, this is going to come.
Does it reflect it with the y-axis?
Not the y-axis, it reflects
The
over
origin.
something.
Y over X.
Say it again.
The origin.
Not the origin.
Thank you.
What was it, Tony?
Y equals X.
Well, y equals x. It's reflected over the line y equals x. So y equals x is this diagonal line. Y-intercept 0, slope 1, right?
Oh.
The inverse is the reflection over that line.
See, that's what I was trying to do.
So this would be
Notice.
F inverse. Okay. Now, that's sometimes hard to do though. It has that symmetry. You can always just reflect one over that line and it gives you the other. But it's a little bit difficult to do visually. I've got another recipe for you that you can use instead. This is kind of a weird one. I've never seen this in a book or anything, but I guarantee it works. It works every time. And here's the other nice thing about this. We sort of present this as though there's something special about the blue graph. That's where we started, and the red one is the inverse. Is that so?
No.
No. We could have started with the red one, couldn't we? Because all the inverse says is that you're interchanging the domain and the range. The domain of one is the range of the other and vice versa, right? So it doesn't matter which one you call the F and which one you call F inverse. They're just inverses of each other, right? Here's how you can generate the graph in a way, a two-step way that I think is a little bit easier to do visually. Step one is, we'll just go from blue to red, how about? So start with the blue. Step one is you're going to rotate the function 90 degrees counterclockwise about the origin. Sounds a little weird, but that's easy to do, right? So if I do that to the blue graph, I'll just get something like that, won't I? If I just put a tack in the board and spin the whole board 90 degrees.
Yeah.
Agreed? Step two is you reflect it over the y-axis. Okay. And you can see if I reflect the light blue one over the x-axis, I get the red one. It seems like it's 2 steps instead of 1, but I guarantee you it's easier to do.
You
rotate it 90
it over what?
You
The X, Y.
reflect it over the y-axis, yeah.
Okay.
Okay. So you rotate 90 degrees counterclockwise and reflect over the y-axis. Okay? And you can see it worked for the red too, wouldn't it? If I rotate the red 90 degrees counterclockwise, I end up with that. Whoops, I end up with this, right? Reflected over the y-axis, so I get blue. Right? Yeah. So I'll go. Let me get rid of the last two. There we go. Anyway, that's just kind of an alternate way of manifesting that symmetry and creating the graph of the inverse. Okay, so we know what the graphical relationship is. We'll come back again in a little bit and look at the calculus graphical relationship of that. But we're still in review mode. So let's try something like this now. How about, let's go ahead and take this problem we just had and let's solve for the inverse function. Okay? So, quick definition before we do that. F of x and g of x are inverses, okay, if and only if. Inverse functions now, right? We're going to jump up to functions. If and only if. That's what IFF means, if and only if.
Oh.
F of g of x equals x, and g of f of x equals x, if they undo each other, okay? Now, real quick, listen, just for a second, I want to jump back to this graph. Okay, here's my question for you. And then we'll move forward just a second. The blue relation, is that a function?
Yeah.
Okay, is the red relation a function?
Yes.
Yes, they both are. They both pass the vertical line test, don't they? Okay. Let's try this again. Let's try a different function here. How about this one?
Okay, so.
Yeah.
Let's graph y equals x squared. Okay, now let's generate the graph of the inverse. Okay, so I gotta rotate it 90 degrees counterclockwise, so it ends up over here, right? And then reflect it over the y-axis. So doesn't it just end up doing this?
Heck yeah.
Okay, so blue graph function?
Yes.
Yes. Red graph?
No.
No, not a function. Okay, let's see if we can explore a way that we could have predicted that. So the blue line is a function because it passes the vertical line test, right?
Yes.
So if I pass a vertical line through this anywhere, and that'll be our representative vertical line, it only intersects once,
Oh, yeah.
right?
But it passes horizontal.
Okay, yeah. But now let's go ahead and let's go ahead and reflect that vertical line also to create its inverse at the same time that we're creating the inverse of the red function, or the blue function, right? See what I'm getting at? If I rotate the purple line also, don't I end up with a purple line down here? That's its analog,
Sure.
right? Not vertical anymore, horizontal. See my point?
Yeah.
Okay. Point is that if I had grabbed the vertical line that represents the failure of the red graph in the vertical line test, if I reflect that over y equals x, or however you want to do it, if I graph its inverse is going to be horizontal, right?
Yes.
I said that in a really kind of
So the
clumsy way.
horizontal line test is like the inverse test.
Exactly. So a vertical line test for one of the functions, in other words, or one of the relations, corresponds to a horizontal line test for the other, right?
Yes.
So the fact that this green line, this green vertical line represented the failure of the red graph in the vertical line test, so it's a non-function. If I reflect that back, it manifests as a horizontal line for the blue graph, right? So the point being that we could, even though the blue relation passed the vertical line test with flying colors, it is a function. It fails a horizontal line test, and so that predicts that its inverse will fail the vertical line test, right? Okay, so then if we want a function, we want to have a function that has an inverse function, it has a stricter requirement. It has to pass 2 tests instead of just 1, right? It has to pass both the vertical and the horizontal line tests. Okay, make sense? Okay? It does. We good? Any questions on that?
Yeah, so does that mean that neither are functions?
No. The blue graph, the requirement for a function, all it is, remember, is just that for every input value, for every value of x, there's only one value of y, which just means it passes a vertical line test. If I choose a certain x value, a vertical line will only intersect the function in one place, because there is only one y value for the function, for that one x value. So if a graph passes the vertical line test, no question, it's a function. The blue one is, right?
Yeah,
But the red one is not.
okay,
We could have predicted that the inverse of the blue one will fail
by the horizontal.
by the horizontal line test.
Okay.
Exactly, okay?
Gotcha.
All right, so now let's go back. We know we've got this test for functions. We know that if f of x and g of x are inverses, then both of these things have to be true. The composition of f of g of x has to equal x. In other words, they have to undo each other in that direction. And g of f of x also has to equal x. So they must also sort of undo each other, right? Let's go back to the original graph here that we looked at. And the blue one was x cubed, or y, yeah, x squared, or x cubed, right? Y equals x cubed. So let's calculate the graph, or calculate the inverse that goes with that. In this case, it's a function, right? See if this rings a bell. F of x equals x cubed. Hopefully you remember doing this. So step number 1, we always said, was you trade the f of x for a y. So write it in terms of x's and y's. What was step 2? Keeping in mind that inverses, the definition of an inverse is you're just swapping x's and y's.
So,
Switch the x and the y, there you go. So step 2 would be you switch the x and the y, and then what? Yeah, you solve for y. Solve for the new y, and the result will be the inverse, right? So in this case, I solve for y by just cube rooting, don't I? Right?
Yeah.
So I get y equals cube root of x, and that's what that graph is. Okay, make sense? Now, this is where, math is just so cool, because it all just kind of comes together, and it's all so self-consistent. All the things we've been talking about, which had really nothing to do with specifics of functions, it was just graphs. That makes sense, doesn't it? This is a function, and that's a function, and there's no problem there, right? Both of those pass the vertical line test, okay? Let's take this example right here, though. I gotta clean this up a little bit, my goodness, we got stuff everywhere. Here, I'll just redraw it. So this time we're starting with y equals x squared. Let's make it f of x equals x squared. And we know what the inverse looks like. Looks like that. Let's do the math though. If f of x equals x squared, what's our recipe? Square root, or write it in terms of y. Change the variables. So what's y equal to?
Square root of x.
Not exactly.
Plus or minus square root.
Plus or minus. Okay, and that's important. Okay. Okay. So then is square root of x, well, let's test these and just see if they are inverse functions. So over here we got cube root of x and x cubed. Let's check and see if they work. In other words, do they undo each other? Do they pass the test for being inverse functions? So is f of g of x equal to x. Well, let's see. So we're gonna get f of x is x cubed, so f of hand is hand cubed, right? And f of g of x would just be g of x cubed, right? So I've got, and really cube root is just 1/3 power, isn't it? Right. Oh, we'll write it as root. So it's more obvious. And what's that answer?
X.
Check. That one checked off, but it's gotta work the other way also, right? So. So let's try the other way. Is the cube root of, oops, x cubed equal to x? Yeah, it is. Check, check. Pass both the tests. They are inverse functions. Easy. Okay. How about this guy? Well, let's check this one out and see if it works. Okay. So f of g of x would just be the square root of x squared, right? And then g of f of x would be the square root of x squared. Okay. Right? What's this equal to? That equals x. That does equal x. What's that equal? By definition. Okay, so they are not inverse functions taken as a whole. Okay, this is all consistent though. This is all consistent. We kind of could have predicted that because of that outcome, right? The math gods did something really helpful here that we just sometimes we don't give them all their due credit. The math gods told us that, yes, the math gods told us that the red inverse is broken into two separate pieces. Now, taken individually, those two pieces are functions. Think what that means. If we say plus the square root of x or minus the square root of x, what does the plus the square root of x look like? Yeah, that's just the part on top of the x-axis, isn't it? So the green part, the plus part, is this part right here. Right? Now the minus part is the part below. Taken separately, they work, don't they? If I just take the green, that passes the vertical line test, or if I just take the red, that passes the vertical line test, right? Okay, now I can treat them separately like that, but what's the inverse of the green part of the square root? So the inverse of positive square root of x would be which part of the blue graph? The right. Yeah, it's only the right part, isn't it? Right? So we'd have to just isolate that part right there. Okay, so in other words, the square root of x, the inverse of the square root of x would just be y equals the cube root of x with the restriction that, I'm just going to, oh my gosh, I'm thinking about different example. The inverse of the square root is y equals x squared with the restriction on the domain that what? What's the domain of the light blue section? Yeah, okay, where x is greater than or equal to 0, right? That's going to go with y equals the square positive the square root of x, right? What's the range of the square root of x? 0 to infinity, right? I mean, if we were to graph these things, if we were to look at the ranges and the domains of those, here's my point. This is kind of cool. So if f of x equals the square root of x, where x is greater than or equal to 0, and g of x. I did it backwards, didn't I? Oh well. Oh my god, I just really screwed up. This is what I meant. X squared, right? Blue one was the parabola, where x is greater than or equal to 0. And the red one that went with it was positive the square root of x. Look at the domain and the range. Okay, the domain of the blue is what? Light blue. I mean, that, right? X is greater than or equal to 0. What about the range? Y is greater than or equal to 0. Okay. Okay, so doesn't that mean then by definition that the domain of the inverse has got to line up with the domain, with the range of the original, right? And the range has to line up with the domain of the original? Which of course it does, right?
Yes.
What if I took the other one? If I took the other one, it's going to work too, isn't it? If I take the red part of the inverse, that lines up with the dark blue part. Those are the reflections of each other. Okay? Get the idea? Okay? All right. So now, let's look at one other little issue here. How about, where's my original, I guess this is the one I want right here. Oh, that's so messy. Look at those. How about the calculus? Make a prediction for me. If I look at cousin points here on the inverses, so here's my line of symmetry. Right, the line of reflection. What do I mean by cousin points? Like if I take, for example, the point on the function, original function, that has coordinates x1, y1, what's the cousin point?
Cousin?
Okay, it's going to be the cut, meaning the reflection over the line, right? It's the inverse. If I reflect that point over this line of symmetry, there's the point that goes with it where I've interchanged the domain and the range. So the coordinates of that point are just going to be what we call down here, y1, and what we called x1, right? Whatever those numbers were. Okay, agreed?
Yes.
So we know that. What about the slopes? What do you suppose is true of the slopes? If here's the slope of this line, I picked kind of bad points because the slopes look pretty similar. Maybe if we pick some other points, that would be a little easier to do. What if we pick this point right here, how about? Where we get that slope or that slope?
Parallel.
Any projected, any possible, you're not gonna know the answer, but use your intuition here and see if you can tell me. If I take cousin points and I look at the slopes, are they related, do you think?
Yes.
Yeah, you can see a relationship sort of building, can't you? If one of them is positive, the other one is positive. They always have the same sign, don't they? Even if I take like this point right here, and its cousin point like right there-ish, right? Okay, if one of them is, one of them is typically steeper than the other one, right? Any ideas? If the x's and the y's have been interchanged, here's kind of a hint. Slope is defined as rise over run, isn't it? Okay, so yeah, what used to be that we define the rise as the change in y and the run as the change in x. But if the x's and y's are being interchanged, we're literally just what used to be the rise over the run would become the run over the rise of the original, wouldn't it? See what I'm saying? So does it make sense then that the slopes ought to be reciprocals?
Yeah.
And they are.
Ah,
They're
yes.
reciprocals. Okay, now that allows us to do something pretty cool. We know that if, whoops. I'll write this way. So,
Yes, so that means that. So that
Oh, I think so.
Okay, so the derivative of the inverse of a function is equal to the reciprocal of the derivative of the function. But remember that the points, that the x values, in the picture that we drew, the x value here is the y value there and vice versa, right? Does that make sense?
Yeah.
We've interchanged the two values. And so if I'm trying to find the derivative of the inverse at a certain value of x, I've got to take the reciprocal of the derivative of the function at the other point, which would be the y value of this point. See what I'm saying? Right? Because x and y are interchanged. So when I write out this relationship then, right there we go. There we go. Instead of an x, what do I need to put there?
Y.
Y. And so y is y is really it's the y value of the original function, right? Which we could just write as f of x, right? The x value of the inverse corresponds to the y value of the function. Perhaps I should call this a g. It's just too many f's up there. Huh? F and g are inverses, let's say. So g prime of x would be 1 over f prime of f of x. Okay, the point that goes with x, right? That's helpful to us, because sometimes a function, it might be really difficult to calculate the derivative of an inverse. Maybe you can't even do it, maybe it's not even differentiable, but we can kind of sneak around that and calculate the value of the derivative at a certain point by just using this formula. Okay, so an example would be, what if we had something like this? What if we want to wrong example. We'll just use this function though. Oh, that's too hard a function to differentiate. We're gonna make an easy one. Not much time. We'll just do a polynomial. Okay, the goal here is to find, we want to find the derivative of f inverse at 3. Okay. What are our choices? Our choices are, we could go through the whole process of calculating the inverse, which sometimes can be kind of tough to do, and then differentiate that function and evaluate it at 3, right? Plan A. Plan B, skip all that. Use this formula. This is equal to 1 over f prime, which we have, right? F prime of what number? Well, we do have to calculate that. It's going to be, if we're trying to calculate the inverse at an x value of 3, we have to calculate the reciprocal of f prime at the y value of the inverse, or y value of the function, right? The x value of the inverse is the y value of the function. So what goes there? The value of f of x, when x is 3, right? That's got to be, in other words, this just has to be f of 3. See? Okay. How do we find that?
You plug
Plug
it
it
in.
in.
Plug it in. Right.
Plug it.
We're just gonna, that make sense? We're gonna plug in 3 for x and just see what we get. What do we get?
Well, that's tough.
Yeah. What do we get? I'm just gonna cheat and look. sorry, look what I did here. It's gotta be, it's gotta be G, doesn't it? I did it wrong, right,
Oh, boy.
right? It's gotta be, we have to analyze the derivative, f prime, not at x, we gotta analyze it at the other point that goes in this one, right?
Yes.
Right, so it would be when y is 3 for the function, right? X is 3 for the inverse, is y is 3 for the function, so we're really just doing that. Right?
You're all wrong.
Right? Does that make sense?
So the answer.
The x's and y values have to go together, so this is the x value for f prime, the x value has gotta be the y value for f of x, okay? We can't really answer the question, what the y value of we have to work with the function because we haven't even calculated the inverse yet. So we would just solve this equation. If I add 1 to both sides, I get 4, right? And then if I solve this thing, I'd subtract 3 and get a 4, and I've got a quadratic or a cubic equation. If I do that equation and I solve it, we're not gonna take the time to do it. If I do this, we just get the answer, x equals 2. We can verify that. If I plug in 2, we just get 8/4 is 2, plus 2 is 3. Is that right? Did that work? No. It didn't work. They were wrong.
Oh, they
The
suck.
book is wrong.
Did I write it down?
Why?
But.
That's right.
They're wrong. They said 2. That's not right, is it?
X is 2. 2? Yeah, it is, it's right.
Yeah, but.
Oh, no, it's right. Isn't it?
Yeah, it's 2.
2.
And it says 2.
Plus 2
I don't know
is
what it is.
6.
2 plus 2 minus 1.
Oh, that's right. That's right. 2 plus 2 is 4, minus 1 is 3. It works. Okay, so there's the x value that goes with a y value of 3, right? And so that's what we're gonna evaluate the derivative at, right? So we do have to take a derivative, but we know the function, so taking a derivative isn't that big a deal. And isn't this a much easier function to work with? Now think what its inverse would look like. That's a nice polynomial, the easiest, most friendly kinds of functions to deal with. The inverse is gonna be some convoluted combination of roots, right? We're gonna end up with cube roots of, it's gonna be complicated, right? This is really easy to evaluate too, and easy to differentiate. So f prime equals what? So we just term by term, we bring the 3 down, we get 3/4 x squared plus 1, and then 0. So if that's f prime of 2 equals 3/4 times 4 plus 1, so see if I can get this right. So that's 4, right? Everybody agree? 1/4. Make sense? Okay, I bet it does. Let's do one more so it does for sure. You do this one. Okay. Okay, let's do this. So we'll do an easy one. So how about this? Here's f of x. Okay, let's calculate the derivative of the inverse of that. Let's calculate the derivative of the inverse at 2, right?
1 over f prime of g.
Okay, good, so let's calculate f prime. What's f prime?
2.
2. Okay, this is a pretty easy one, isn't it?
Yeah.
because I'm supposed to calculate 1 over f prime of the y value that goes with that, right?
1/4.
And so I guess technically, we were supposed to put, this function equal to 2 and solve. But what is the derivative? Is it a function of x? No, it's just a constant, isn't it? It doesn't even really matter what value I'm plugging in there, because f prime of anything is the same. In this case, f prime is just 2. So the answer is
2.
1/2, right?
That's embarrassing.
1/2.
Okay. How about this guy? How about yeah, let's try that. So g prime of 2 is going to equal 1 over f prime of what?
2.
Not 2. Right? 2 is the x value for the inverse. The x value for the inverse has to be the y value for the original,
So you
right?
get a derivative of x equal it to 2, figure out what that is.
Oh, we set the f of x equal to 2, right?
When
See
you
what I'm
use a
saying?
derivative.
So the 2, does that make sense? The 2 that's going into the x value for the inverse has to be the y value for the original. So that's what we're setting f of x equal to, right? Right? So what's the answer?
Fifth root of 2.
Fifth root of 2. Okay. It's an odd roost. Do I need a plus or minus? No, one answer. Fifth root of 2. What is f prime?
4x to the, 5x to the 4.
So then, if I evaluate f prime of that number, I just get 1 over 5 times
Square 5 to
our number, right?
So
Fifth root of 2 to the 4th. That's our answer. Right? So 5 times 2 to the 4/5 on the bottom.
Oh,
Get it?
yeah.
Okay. Well, I'm not gonna have time, it's to do a really big example of this, but this is really cool. This is consistent with, in math, you might remember several times we've talked about how important it is to be able to kind of change pictures, to grab a different picture to do a complicated something and then shift back. Like in calculus, we do it all the time. We make u substitutions, right? We've got some complicated integral, and so we're gonna make a tradesy. We're gonna make a u substitution, get some new function that's easy to integrate, get the answer, and then shift back, right? People do this in, these smartest guys in the world with huge foreheads do this when they're computing, they're trying to link up physical relationships in the universe to string theory. They do this stuff all the time. They take these 7-dimensional Calabi-Yau spaces and transform them into a different, using this intense topological math. They'll make this transition and manifest the thing in one way to figure out what gravity is, what's causing gravity, and then they'll rotate it back and they'll flip it back and they'll put it in a different space to try to figure out what's causing all these little fermions, what represents that. And they're always doing these big, huge tradesies, but it's the same idea. They're just gonna trade from one manifestation to another to get an answer and then trade back, right? A lot of times that's easier than having to use this kind of a symmetry, than having to go through the brute force of calculating the inverse, which might be tough, differentiating and evaluating the derivative. We'll just use the symmetry of the fact that they're slopes, that the derivatives are just reciprocals of each other, right? Symmetry is it's the greatest saving grace and trick in the world in math. Saves a lot of hard work. What's that?
You're right, shoes and tie.
Oh, it is. You're right. Thank you.
Gotta look out for my teacher.
That's right.
I want you to fall